Okay, let's start right here. This is where we left off. Yes. Thank you. Thank you. No, it's not. This is where we left off. Okay, think about where we left off with the photoelectric effect. Anybody have this word in your notes? Should be from yesterday. The photoelectric effect is the work of Max Planck and then Albert Einstein a little bit further on. And this is all going to tie together. All these guys are working at the same time, so it's not like one individual. We're in the 20th century now, the 1900s. If you remember, Max Planck was back here, and he was like 1900 or so. Yeah, it's not on the screen. But we're in the 1900s. People are communicating now pretty quickly. We don't have telephones or cell phones yet, but we definitely have telegraph systems starting to transfer information. So if you're working in one part of the country, you can communicate pretty quickly with other parts of the country. This has resulted, by the way, this is one of the main reasons in the last 100 years that science has exploded, is because communications worldwide, first through the telephone system and then through the internet, has made communications so much more ridiculously fast. So if somebody discovers something in China, some guy working in a laboratory in China, within a day, everybody in the world knows about it, and they say, wow, if that's true, then this must be true. If this is true, we can do this experiment. If this experiment works out, then we can do this experiment. And that's why you see so much new stuff every year in science, in technology, in electronics, in chemistry, in physics. It's just exploded in the last 100 years. The faster the internet gets, the faster that information spreads. Okay, so the photoelectric effect. Einstein's the guy that sort of came up with the idea that, well, particles, light can act like a wave as well as a particle. I think we got this yesterday as well. And we talked about a photon. We looked at this formula and said, hey, that's exactly the same formula that Max Planck gave us for the energy of a quantum. So if this is the exact same formula for the energy of a quantum and the energy of a photon, what does that tell me? A photon holds what? One quantum of energy, right? And so there's a number associated with that. Energy is always absorbed or given off in certain increments of photons or certain increments of a quantum. Now this is a bizarre idea. In the 1900s, it's still a bizarre idea today. People don't picture, Houston, light traveling as particles, right? You picture light does not push you. I can't shine a flashlight at you and push you away. It's not without going to science fiction, right? We don't have ray beams or energy beams like that. So we don't picture energy as having the ability to push something. But this would be true, okay? If photons act sometimes like mass and sometimes like energy, then they are weird, okay? And so this is today this is an accepted fact. But in the 1900s, early 1900s, this was like blowing people's minds. And a lot of high school students don't think about this every day. You get to because you're taking chemistry. Okay? Okay, on this slide here, I want to point out two things. Question? Okay. Your book uses the illustration of a neon sign to talk about how atoms can get excited. But up here in the upper right-hand corner, I wrote two things that I also want to remind you about. Our flame test lab and fireworks. Fireworks, flame test labs, neon signs. All three of these are great examples of how light is given off when we do something to the electrons in the atoms. In the case of your flame test lab, we used a Bunsen burner. We got them up to about 500 or 600 degrees, and we got those electrons to absorb some energy from the fire, and they gave off light when they gave up the energy. Fireworks do the same thing. They use the gunpowder to basically burn some elements, and they change pretty colors in the sky when they give that energy up. Neon lights, like our Crookes tube from chapter 4, does the same thing. Neon lights are going to absorb energy from electricity, and they start to glow a certain color. Most neon lights are orangish in color because that's the color that's given off by neon. You might have seen green neon lights. They have a different chemical inside of them rather than neon. So technically they're probably not neon lights, or they have neon with some other chemical mixed in. But this is because atoms can pick up energy through their electrons, and when they give it up, they give off light. Okay, so these are 3 examples: neon lights, fireworks, flame test lab, of how electrons pick up and give off energy. Now let me talk about that for just a second before I go to this. Everybody remember last year when you talked about potential energy and kinetic energy? Everybody remember this? Okay. And so if I hold something like this above the ground, it has potential energy. How much kinetic energy does it have right now, Brinkley? 0, because it's not moving. Okay. The minute I drop it, it starts to gain kinetic energy. And it takes the potential energy that it has right now and converts it into kinetic energy. When it hits the ground and stays there, all of the kinetic energy is gone and all potential energy is gone. And it's at its lowest level. So what we're seeing, electrons do the same thing. They can gain energy, potential energy, and when they drop back down into a lower state, a lower level of energy, they give up that energy. They give it off as kinetic energy, and it turns into photons. So going back to Max Planck's work and going back to Einstein's work, they noticed, and this is actually, let me double check here. Okay, so this is actually a picture of a spectrum. Here's the key word on this slide, spectrum. A spectrum is like a fingerprint. Okay, every person on planet Earth has a unique fingerprint. But in chemical terms, every element up there on the periodic table has a unique fingerprint, and it's called its atomic emission spectrum. Now, you say, what is it? Does it look like whirls? Does it look like all my little bonus point things with the whirls and the swirls and the double tents, and there's names for all these things over here on fingerprints? No. The spectrum here for elements consists of a number of lines, and each one of those lines consists of a frequency and a wavelength. Frequency and wavelength, and those frequencies and wavelengths correspond to the energy of the electrons. So for hydrogen, for instance, there's one here, there's a line here at 410 nanometers. That would be a wavelength, right? And there's another line at 434 nanometers, and another one at 486, and another one at 686, and actually there's a couple others that go higher than that. So along comes a guy, okay, and the word for this is atomic emission spectrum, and again we can measure this using a prism and something called a spectrograph, and it actually prints out what the spectrum is for a certain kind of light. Who uses this a lot? Astronomers. Anybody love astronomy? You go study astronomy, you're going to see that astronomers can take the light coming through a telescope, put it through a prism, and make a graph that looks like this. Atomic emission spectrum. This is how they tell what elements are in a certain far-off star. Mostly hydrogen, but there's going to be some other elements in different stars. That will give some stars a blue color, some stars a red color. We have called red giants, and we have blue dwarfs, and we have brown dwarfs, and we have super yellow giant. I mean, there's all kinds of different stars out there. They have different characteristics of their spectrum. Cool? So every element, hydrogen has a spectrum, helium has a spectrum, lithium has a spectrum, carbon has a spectrum, and it's unique. Each element's atomic emission spectrum is unique. Again, I call it a fingerprint because it is unique to that element. Okay, that's the end of section 1. Review question 1. Smallest amount of energy gained or lost? JP? Quantum. Nicely done. Point, point, point. And Peyton, what is a particle of electromagnetic radiation called? Yeah, rule that one out, and we already used this one. So photon is the particle of energy. Okay, I call them chunks. The official word is a photon. The generic term is called a quantum. They're essentially the same thing, but we think of a photon as the particle of electromagnetic radiation. Okay, Now this just continues. Section 2 of this chapter just continues talking more, and we're going to go into Einstein. Einstein was, remember, working on the fact that these little particles sometimes act like energy, waves, sometimes act like matter. They have mass and momentum and kinetic energy. Okay? Two different things, guys. Okay? You get hit by a truck, you know it, because a truck has momentum, a truck has inertia, a truck has kinetic energy, a truck has force. You get hit by a beam of light, and you're not too worried about it, right? But Einstein eventually took this idea and came up with this famous equation, E equals mc squared, and said energy and light are two parts of the same thing. Wow, that's loud. Here's where Bohr comes into play. It's 1913. Hello? Yes. Adriana, early discussion. 1913, Bohr shows up, okay? Not shows up, he's been working behind the scenes. But he is working in Rutherford's lab, and he comes up with a new model for the atom, okay? And again, in chapter 4, what did we say Bohr, what did I relate to Bohr? Bohr got, on the matching section, the only thing I gave you for Bohr was what? Looking for a hint of recognition here. Somebody help me out, raise your hand. Bohr? Kendall? Okay, electron shells or energy levels is what I call them. Both of those work. Okay, so Niels Bohr, chapter 4, we said was responsible for energy levels. Here's where we show you how he got involved. Okay, so he's working with hydrogen. He's doing experiments with hydrogen. He heats the hydrogen up. He measures the spectrum that's given off. And he actually develops a model to predict 7 different levels that the electron, how many electrons does hydrogen have, Michael? Just one. So it's a real simple model that he's working with. So he heats hydrogen up, he measures the amount of light given off, and he finds out that hydrogen has different energy levels. I'm going to back up here. I want to point something out. Okay, the lowest allowable energy for any atom is called its ground state. And that's really easy to remember. Alex, if you're laying on the ground, how lower can you go? You can't. You're at the lowest possible point if you're laying on the ground. And that's why it's called the ground state. This is the lowest possible energy somebody can have, is laying on the ground, not doing anything. Okay? Now, if you're above the ground, we just said before, we got potential energy. We can do something with that energy, right? So if I'm above the ground, I am in an excited state. Excited means you got some energy. Everybody with me? Okay, so here's my illustration, okay? A lot of people on Sunday afternoon or Saturday afternoon, they've got the TV on, they got their favorite football team playing, and they are just relaxed in the easy boy chair, lazy boy chair. Got a bag of chips, maybe some onion dip, can of Coke, some sweet tea, remote control. I am in my ground state right here. Just relaxed. Football game's going on, kind of goes off a little bit. Right? Until what happens? Until he throws a 50-yard bomb to the end zone. Until there's an interception and your team gets the ball back. Until there's a fumble and somebody picks the ball up and all of a sudden you go, whoa! And you jump out of your chair and the chips go flying everywhere and you go, oh yeah, oh yeah, oh yeah, there. And everybody says, what's going on, what's going on? They come in from the other room and they go, oh yeah, you should see what happened. And they show the instant replay. All of a sudden you're in an excited state. You're no longer in the ground state over there. You got excited. Things have changed. You look different. You're giving off a different vibe. And you have got some energy to give off, right? See the difference? So electrons here look one way, and electrons here look another way. They have a whole different frequency and wavelength. And that's what electrons do when they bounce up to the next energy level. Now, there's even another energy level beyond the first excited state. You're in overtime. You're tied. You're going down to the final minutes. and the tension's building, and then at the very last second, we won! And he's like, I mean, an overtime game is like, whoa, that's above and beyond a fumble recovery, right? That like, yeah. And then a couple weeks later, guess what? You go to the 4th energy level. It's like SEC championship. Whoa! Yeah, and you win the division or whatever, and it's like it's you're running around outside on the front lawn, and you got banners strailing behind your car, and you come into work with your face painted. I mean, you got level 4 of energy and level 5 of energy. Okay, different levels, different characteristics. And when you got to give off that energy. If you don't give off that energy, you're just going to pop. Okay. So electrons do the same thing. They have different amounts of energy, and it's literally the potential energy to give off photons. And so Mr. Bohr came up with this idea. He says, my data shows these electrons can give off energy, absorb energy, and he likened it to what you and I call orbits. Okay? And this is the word I used way back when in chapter 4. Recognize it now. Now this makes sense. If we do the physics of this, we will know that it takes more energy for something to orbit out here than it does for something to orbit in here. Okay, the closer we are to the where did you go? Where did you go? Okay, so the closer we are to the nucleus, don't go there. The closer we are to the nucleus, the less energy it takes. The farther away from the nucleus we are, the more energy it takes, okay? And so Bohr came up with a model that fit his data perfectly. And it was that the higher energy levels meant that those electrons were further and further and further away from the nucleus. Rutherford had already figured out the nucleus. Nobody knew where the electrons were. So Bohr, he's got a great idea. Today we know it's not quite this way, but he had a great idea. He says orbits, energy levels, electron shells. Now, he called these orbits quantum numbers, okay? We call them energy levels or electron shells, like Kendall mentioned just a minute ago. And Bohr's work showed that for hydrogen, there were 7 different ones. 1, 2, 3, 4, 5, 6, 7. Each one with a different amount of energy, which corresponded to a different radius. Notice the radius is 0.05 all the way up to 2.5, a factor of 100. Some of those electrons could be as much as 100 times further away from the nucleus than the inside ones. So all of a sudden, our model of the atom is getting very complex. Now, I want you to take 2 things away from this chart. Number 1, there's 7 and only 7 possible energy levels. And those 7 energy levels correspond to these 7 rows on the periodic table. Notice there are 7 periods, and this one starting with francium is the 7th one. And that's not a coincidence, okay? We'll talk more about that later. The other thing I want you to notice is the amount of energy needed to go from level 1 to level 2 is not twice as much. It's 4 times as much. And to go from number 1 to 3 is not 3 times as much, it's 9 times as much. And then it goes 16 times to level 4, and 25 times higher for level 5, and 36 times higher for level 6. Does anybody see the pattern? Okay, we call this a geometric progression, where every number is squared. So level 2 squared, 4 times as much. Level 3 squared, 9 times as much. Level 4 squared, 16 times as much. And that makes sense when we think about this. Right? So the amount of energy is related to its velocity squared. And that makes sense. We're talking about little electrons zipping around with a certain velocity. The faster they go, which means farther away from the nucleus, then the more energy they're going to have. Good? So now we're Bohr. Bohr's model falls into place, 1913. This is just a picture of Bohr's energy levels. Energy level 1 to 2, 2 to 3, 3 to 4, 4 to 5. If he heats up hydrogen and releases energy. The colors you see, the spectrum you see, depends on which level we start at and which level we go down to. Whether we're going all the way down to ground state, or from level 6 to 2, or 4 to 2, or whatever. Okay, so there's a different amount of energy given off to go between each of these different energy levels. Okay, so Bohr's work was good. He worked with hydrogen. If you put energy into those hydrogen atoms, he can go up to energy level 2 or 3 or 4. But it didn't explain any element except hydrogen. Unfortunately, he couldn't make it work. He couldn't figure out the math for anything other than hydrogen. And even though the behavior of electrons was not still fully understood, Schrodinger hadn't come along yet, Heisenberg hadn't come along yet. Okay? Today we know they don't really work in circular orbits. We're going to cover that tomorrow. But Bohr's model explained hydrogen spectral lines, but failed to explain other elements. Just know that there's a failure in Bohr's model here. Okay, a weakness. I wouldn't say a failure, but a weakness. Okay, so one more guy to add today. Louie De Broglie. This is his last name, so he comes with the DE, which in French means, I think, from, right? Louie from Broglie. And he is a Frenchman who hypothesized, I believe he's a Frenchman, I'm not sure, but who hypothesized that particles, including electrons, could also have wave-like behavior. So I'm going to give you this word association. De Broglie gets credit for the wave-particle duality. Now, we saw that Einstein was involved in this process. We saw that Planck had laid some groundwork in this process. We saw that Bohr was involved in this process. So there's a lot of guys working on similar stuff here, but De Broglie gets the credit for wave-particle duality. The fact that a single electron sometimes acts like a particle, sometimes acts like a wave, a chunk of energy. And that's going to be important to talk about tomorrow. Including that video. We'll start with that video tomorrow, which is a really cool summary of everything we're covering the rest of the chapter, which gets even a little bit more complex than what we're talking about here. Okay, everybody understand the fingerprints? Okay, spectral lines are important. And if you ever read the stuff in astronomy textbooks, and I've got about 6 astronomy textbooks down there if anybody's interested, you'll read a lot about spectral lines. And they're not spectral like, Halloween spooky stuff. Spectral like the lines in the spectrum. Good. Good place to stop. Questions?